This question is from AP Physics 2, and they say that in a certain metal, the stopping potential of the emitted electrons is found to be 4 volts. When 200 newton light is incident on the metal, electrons are emitted. What is the work function of the metal? And then find the de Broglie's wavelength of those emitted electrons. So to find the energy of the photons, I have to use the formula where I have E is equal to the Planck's constant times the frequency of the light that is incoming, or we have the Planck's constant times the speed of light divided by the wavelength of those photons. And that one is given. So I have, I'm going to plug in the numbers in electron volts. So the Planck constant is 414 10 to the negative 15 in electron volts. And then the speed of light is 310 to the 8. And the wavelength that they give you is 200 nanometers, which is 10 to the negative 9. If I do my calculations, I will get 6.21 electron volts. So this is the energy of the photons that are coming in. So that means this number for the energy would be 621 electron volts. The energy that is left in the photon, in the electrons after they have been emitted is given, and that is can be calculated by using the formula. So the work done on the electrons is equal to the charge of the electron times the voltage. And if I keep the electrons as charge as E, it times it by 4 volts, I will get the energy or kinetic energy of the electrons after they have been emitted equals to 4 electron volts. So that is the kinetic energy of the electrons that are leaving the metal. So these ones are 4 electron volt energy. They carry 4 electron volt of energy after they leave the metal. And I'm going to rewrite this in purple so they match the colors. Then I can use another formula where I know that the energy that is coming from the photons is going to be used or spread between two types of energy, which is the work function needed to pull out electrons from the metal plus the kinetic energy of those electrons. So if the energy of the photons is equal to 621 electron volts, and the kinetic energy of the electrons after they have been emitted is equal to 4 electron volts, then the work function to pull out those electrons from the metal must be equal to 2.21 electron volts. So this answers the first question, what is the work function of the metal? And for the next question, I have to find the de Broglie's wavelength. So the kinetic energy of the electrons that are emitted has the energy of 4 electron volts. I'm going to convert that kinetic energy into joules. So I have 4 times 1.610 to the negative 19. The charge of the electron is 1.610 to the negative 19. And I will get the energy in joules as 6.4 10 to the negative 19 joules. And that is equal to 1/2 the mass times the velocity squared. So the mass of the electron and velocity squared. So then I'm going to plug in the numbers. So I have 6.4 10 to the negative 19 equals to 1/2. The mass of electron is 911 10 to the negative 31st. And then I have the velocity squared. So from here I have velocity is equal to the square root of 1.405 10 to the 12, which gives me 1.19 10 to the 6 meters per second. And here where I'm going to use this velocity to calculate the de Broglie's wavelength. So what de Broglie said is that if you look at the kinetic energy of the electrons, electrons can behave as particles or wave. So if they can behave as waves, then I'm gonna rewrite the energy, which is E, is equal to Planck's constant times the frequency. And then if we replace Planck's constant with, again, speed of light over the wavelength, and set this energy is equal to mc squared. If one of these c's cancels, then the wavelength is going to be equal to Planck's constant divided by the mass times the speed of light. But the electrons do not move with the speed of light, so we have Planck's constant divided by the mass times velocity. In other words, the Planck's constant divided by the momentum of those electrons. So for de Broglie's wavelength, we're going to use the formula where lambda, the wavelength, is equal to the Planck's constant divided by the momentum of those electrons. And because we found the velocity of the electrons, we can use it to find the wavelength. So the wavelength is equal to Planck's constant, and I'm not plugging it in electron volts, I'm plugging in meters squared kilogram per second. So that is 663 10 to the negative 34 divided by the mass of the electron, which is 911 10 to the negative 31st, times the velocity of the electrons that we just found earlier, 1.19, 10 to the 6. And so from here, the wavelength is going to be equal to 0.612 nanometers. And that is all I have for this question. Thank you for watching, and I hope I see you in my future videos.